I'd like to welcome everybody here. This is another in the tutorial series, which is really a wonderful way to get to know new material, refresh yourself with material you might have known and forgotten, and sort of get excited about new directions. And it's actually a great pleasure for me because I don't have to do much work. Here's a person who doesn't really need an introduction. But I'll do it anyway. I've admired his work. You probably know any of the products that he's co-developed, Lindo, Lingo, What's Best. But as well, he's now currently associated, has been associated with the booth there at the University of Chicago. And he's a man with many interests, and you're going to find out a little bit about what he's been interested in lately in terms of his talk about multi-period planning. And a lot of the modeling tricks and the insights in which you can kind of take a basic model and then really modify it so it really does closely reflect reality. So without much further, I will make an announcement or two. As you know, as attendees or members of Informs, you get free access to the printed chapters of this. There's as well a hard, soft-bound version if you really want to have a physical book, which is available at minor cost, relatively, there at the Informs booth. But most importantly, you are all part of a grand experiment. Namely, this is the first time in which we are having simultaneously the slides and the speaker's voice synchronized together. And very often, you're going to get additional content and insights that you couldn't get from that reading that page itself. And those, once they will be posted and as well be available at no charge to you. This is a first really for Informs, so consider yourselves as willing experimental subjects here. So turn it over to Linus. A pleasure.
Okay, thank you very much. So sorry for delaying things a little bit. I had a slight adventure right as I was entering. I tried to get onto the platform from that end and tripped and busted my shin. And so if you see a little red spot on my leg, it's because I got a little scuff there. So let's see if we are synced together here. It helps if you turn it on. Yes, that works. Okay, so the official title is A Guide to Multi-Period Planning. And what we're going to be looking at is design and use of optimization-based multi-period planning. If you have any questions or comments, please email me at whichever address you find more convenient. I'd be delighted to hear from you. What usually happens at a survey talk or a tutorial is the speaker tries to go back and show the roots of the topic, and so I will do that here, courtesy of George Danzig, essentially. And he claimed that the history of multi-period planning went back to the Bible, to the Old Testament, in fact. And so you may be familiar of Joseph, who was doing some pro bono work in Egypt at the time. And the Pharaoh approached him and said, I had this dream involving 7 fat cows and 7 lean cows. What does it mean? And can you help me? And Joseph said, yes, I can help you on that. I mean, what it means is that the 7 fat cows correspond to 7 years in which things will be good. The crops will be great. The 7 lean cows correspond to 7 years which will be not so good. They'll be lean. There will be a drought. And so the Pharaoh said, what should I do? And Joseph said, inventories, multi-period planning. So what you want to do is build up inventories during the first 7 years so that they can be used in the years that are lean. And so the Pharaoh was impressed because that is in fact what happened. The multi-period plan worked. And so the Pharaoh said to Joseph, how did you figure this out? And I don't know what accent was used in those days. And Joseph said, well, I used linear programming. So that's the history. So let's That is George Danzig. So, so let's jump ahead a couple of millennia, and there is a paper which is a good one to read if you want to look at the history of the basic ideas. Holt, Modigliani, Muth, and Simon in 1955 were working with a paint company in Pittsburgh. The Pittsburgh Paint Company essentially is, that may not have been their official name. How many of you are familiar with that paper, the Holt, Modigliani, Muth, and Simon stuff? Okay, so I may be giving you the best lecture you've had on multi-period planning. So I'm going to cover a lot of topics, so none of them will be the best lecture you've had, but hopefully the collection will be good. So Holt, Modigliani, Muth, and Simon looked at this problem of meeting fluctuating demand. So it was predictable fluctuating demand. And the paint company folks said they had essentially three approaches for handling that. One, you could track the demand by raising and lowering the workforce. And another thing would be to use inventories like the FIFO did. So it was a fairly simple problem by our standards. So it was for a single product with a single workforce. I don't mean that they were unmarried, I simply mean that there was only one type of labor available. So Holt, Modigliani, Muth, and Simon used essentially calculus to solve the problem. They represented all cost curves by quadratic functions and solved that problem. Hansman and Hess's contribution was in 1960 to formulate the problem as a linear program. And here is essentially the Hansman and Hess formulation, and you don't have to go through every particular constraint, but it certainly gives you the basis for many multi-period planning problems today, with the key feature being the inventory constraints up at the top, and then the workforce constraints, which could also be viewed as inventory constraints for labor. And then there were constraints that you cannot produce more than you have capacity for from the regular time or from the overtime that you introduce. And then the inventory was allowed to go negative, so Hansman and Hess introduced non-negative variables for positive inventory and negative inventory. And then the objective function was simply to minimize the sum of the costs of those things, and it's a matter of striking the right compromise between these half a dozen different ways of handling varying demand. Now, in terms of what motivates us more generally, here are the sort of problems that I'm thinking about when I'm doing this. So they range over things like production planning, supply chains, where some of the big issues are set up and changeover times, also sourcing, which I don't mention there, where you produce stuff. And the period of the planning period could be a day or a week or a month or a year. For Holt, Modigliani, Muth, and Simon, the planning period was 1 month, and the planning horizon was 12 months, 12 years. Another big application is financial models, where the big issues are uncertainty and interest rate effects. In electricity, there's a lot of use of multi-period planning. The planning periods range from an hour if you're planning, scheduling for a day, up to a day or longer. And there's some interesting effects or complications that you have to worry about with electricity generation and hydro in particular. There are ramp-up effects if you're working with things like coal-fired plants. If you're working with hydroelectric production, there may be a nonlinear interaction between water level and flow rate out, so that the amount of power that you can get out of a reservoir is proportional to the level of the water, the so-called head there, and we'll talk a little bit about things like that. Natural gas distribution, there's some interesting nonlinearities there, in that generally you want to store gas close to the demand parts. So in the city of Chicago, there are some underground reservoirs about 50 or 100 miles away where gas is stored. And there's an interesting effect of compressibility, which we'll talk about later, that it's easy to get the first portion in, but it's harder to get the later portions out. It's easy to get the first portion out, but it comes out much slower. So you have to be careful with planning that when the winter comes, you want to make sure your natural gas reservoirs are at high pressure, because there may be a limit on how quickly you can get the stuff out. We'll talk more about that shortly. Resource extraction in oil fields and mines. So the kinds of optimization that I'm talking about here has been used for many years, particularly in precious metals mining, but also in oil production, where you're worried about producing oil depending upon, in reaction to what the worldwide demand is. Staff scheduling, these sorts of things have been used for a long time there in hospitals, etc. And I'll have some examples towards the end of routing over time. The key thing is decisions over time that we're worried about here. Mostly deterministic, but we'll talk a little bit about what you do when there's uncertainty, because that's frequently important. Also, in population models such as forests, this kind of optimization has been in use for 30 years, probably more. Okay, Parkinson's law of modeling, that users will request more detail, more and more detail for a model until the time to solve an n-period model is n periods. So, you can come up with really great 5-day ahead forecasts for weather, but it takes 6 days to get them. So that's an issue here. So if you were in the talk earlier today before lunch, at the beginning, Mr. Laguna pointed out that if you can add little details to a model, it can make the model substantially harder to solve. And so that's going to be part of what motivates me when I'm talking about things here, is that this tug of war between adding more detail to a model and keeping it solvable. So in terms of thinking of how you do approximations, which details you add in, I sometimes think of this hypercube here of all of the dimensions of a model. So there's the supplier dimension, the customer dimension, the time dimension, which was sort of the only one that was in the Holt, Modigliani, Muth, and Simon, and the Joseph and Farrow's model, but you may want to add a products dimension. And if you're dealing with uncertainty, you will add a scenario dimension. So the hypercube gets multidimensional quite a bit. And so we'll talk about, how do you decide what's the size, what's the partition of each of these dimensions, which dimensions should be included. A little bit of review now of multi-period planning models. The basic idea is that you may have sort of a single period model, which may be a blending model, all kinds of different standard models, and they are tied together with inventory variables. And there's usually a double subscript on the inventories. One is the type of inventory, and the other is the time period in which you're measuring the inventory. So once you start thinking that way of the doubly subscripted inventory variable to represent the type of inventory, then you're on your way. And so you have a standard material balance constraint that way. And if you're from a mathematics differential equations background, you may like the last part at the bottom where you say, let's look at the difference in the system state from one period to the next and what controls it. So whichever way is more convenient for you to think about things, please do. So some of the issues that we're going to be talking about are rolling and sliding schedules, types of inventories, attrition and growth. So for example, attrition is an example of a workforce that for most workforce planning, you're going to have attrition. And in some places, the attrition is close to 100%. I don't know what it is with truck drivers these days, but truck drivers in particular, I think, have had a fairly high attrition rate. There's this fairly simple modification to the inventory balance constraint to represent attrition. If you're investing in something, it's just the other way. It's a coefficient greater than 1 rather than less than 1. The if cash is the inventory that you're concerned with. Perishable goods, how do you handle perishable goods? Again, it's this idea of multiple types of inventory. So you have to, that second subscript is going to be the age of the inventory, and so you have to update the age of the inventory. So if you're modeling a cheese firm that sells cheese, you have mild cheddar and sharp cheddar, which is aged quite a bit, few more years. They're interesting decisions of should we sell it now as mild or should we keep it a bit longer to sell it as sharp. We'll look at issues of planning horizon length. Should we plan ahead 1 year, which is maybe typical in sort of mid-range electricity planning, or if you're an oil production planner, they may say we have to plan ahead 60 years, and I'm not sure that they really have to. We'll talk about length of planning horizon later and whether you really have to plan that far ahead, but we'll look at that. End effects, how do you choose the end of, what happens at the end of it? So in the Holt Modigliani Muth paint company example, they had to put some constraints on inventories at the end. Otherwise, what happens if you just chop it off, you'll get the optimal way of going out of business in 5 years or whatever your planning horizon was. So you want to worry about end effects. We'll talk about that. And there are various reasons why you may be interested in steady state models, so we'll talk about that. We'll give some better examples of resource and precedence constraints. And we'll also talk towards the end a little bit about how to present results using various space-time diagrams. A slide or two on taxes and a slide or two on uncertainty. So that's the overview, and let's proceed then. So let's first talk about rolling sliding schedules. And so the way many of these planning models are used is in a rolling fashion or a sliding fashion. I think in the US it tends to be called a rolling schedule. In Europe, maybe sliding schedule. But the idea is if it were the paint company, you would solve a 12-month problem and implement the plan for the first month, and then as new forecasts come in, you slide the whole thing ahead 1 month and you resolve it in that way. So that's the idea. And then an interesting problem there that was pointed out by some of the folks at Naval Postgraduate is what they called model nervousness. And so a model is called nervous if you do this sliding bit and you publish the entire 12-month plan, but then when you slide it ahead to February and you rerun it, folks discover that the plan has changed substantially for February relative to what we said in January. And people don't like that, the folks that interact with you, they say, well, can you make up your mind? And so Brown, Dell, and Wood gave the interesting suggestion of specifying a reference schedule and then using that as a second objective and then solving a weighted combination of those two. So if you put all of the weight on the reference schedule, it will give you a new schedule for the 12 months where the first month of the plan is exactly what was published previously. So if you think you started in January, published a plan for February, and then when you move ahead, you restrict yourself to sticking with the February plan, but going ahead that way. So by varying these weights, you can get the completely unconstrained one or really one that copies things. So that's a nice thing to have in your toolkit to think about. So if any of you want slides, you have the email there. Please send me an email and I will be happy to send you slides later. What else do we want to worry about here? Choosing a planning horizon. So here is sort of the standard obvious suggestion of you solve an end period problem. You look at the solution for the first period, then you add another period to it. You forecast ahead a little bit more. So it's not a sliding schedule, but instead of a 12-month horizon, you use a 13-month horizon and solve it. And so if you get the same solution for the first month, you say, okay, that's good. We probably have a long enough horizon. Well, is that the end of it? Well, it could be that that simple analysis is either too long or too short. How could it be too short? Well, you know, if you had been planning say in December, and so that the last month is November, and you say, let's say October, and the end month was October, and then you add November on, and you say, yeah, there's no change in plan, so we should be good enough. But however, what could happen, if you go ahead to add 2 periods, add December on, then there's a good chance it will change because of the demand spike that typically occurs in December. So that's one way where it might be too short. And a way that that simple rule might be too long is that many of these models have integer variables in them. And what is sort of a standard feature of the solutions to integer programs? They almost always have alternate optimal solutions. And so if you add another month on, it may be just because of computational steps that you got an alternate optimum, which is different in the first month. And so it doesn't make much difference. So a better way of looking at things is say, okay, suppose we fix the first month, add on another period, compare that with when we didn't fix the first month with planning ahead 13 months. Does it make much difference in cost? That's really what you're thinking about, you want to think about. Does it make much difference in cost in the long run if we fix the first month and go with it? Now for the simpler problems, they're lot sizing kinds of problems, there's a substantial literature on identifying planning horizons, and they're all based on this sort of December effect, in that there typically is a period in your demand where things drop off, and as long as you cover at least one of those in your planning horizon, you're probably okay. Okay. So this is sort of a summary of what we're saying there of fix the first period, look what happens, and see if that makes a difference. Choosing a period length. In some cases, it's fairly obvious what the period length should be. So for example, if you're staffing a distribution center or a call center, it's frequently the case that breaks will be 15 minutes long, or all work periods will be multiples of 15 minutes. So the obvious period length is 15 minutes. And so that's what you'll find in many of these workforce staffing models that plan ahead a week or something. It'll be 15 minutes per day. In scheduling of electrical generators for various reasons, it's typically an hour. That is the period length. And that's somewhat related to if it's a coal generator, it maybe takes an hour or so to bring up a coal generator, ramp it up. If it's a natural gas generator, they can ramp up a bit more quickly, like in 15 minutes. But if you have coal generators, which most systems do, you're talking about that length. Now, another observation with regard to period length is that a number of people have observed that you don't have to use periods of constant length. So in some financial planning models, I've seen situations where the first 4 periods are 1 quarter in length, and the next couple of periods are a year each, and then maybe 2 years, and then at the end they do something interesting, which we'll talk about, is you have a final period which repeats forever. And, how do you do that? We'll talk about that shortly, but that has been done somewhat regularly. So let's talk about choosing a period length, and sort of a mathematical approach, which you should have in the back of your mind when you're trying to think about choosing a period length is there, loosely speaking, a greatest common divisor in the activities that are going on in your production plan. So if you're scheduling aircraft to multiple runways, what you want to worry about is a changeover matrix between aircraft of various types. And so, for example, if you're going from a heavy aircraft and then you're having a light aircraft land behind it, you probably want to have well over a minute or 2 minutes of separation. Why is that? Because a 747 or an Airbus 380 creates a lot of turbulence behind it. And so if you're a little Cessna 172 coming in behind it, you're going to have an exciting time landing behind it. And so here are some supposed separation times, a separation time matrix for that. And if you do the greatest common divisor for that matrix, you see that it's 15 seconds. And so a reasonable planning period length, if you were scheduling aircraft for runways, would be 15 seconds. Steady state solutions. So what is a steady state solution? Well, in terms of this initial model that we put up, it's pretty simple. You simply tie the beginning of the model to the end. You say, I don't know what the beginning inventory level is or should be, but I do know I want the ending inventory to be equal to the beginning inventory. And you do that for all of the state variables, and that's how you get a steady state model, a one-period steady state model for essentially any arbitrary multi-period planning model. So one, it's easier to understand if you have a steady state model, and a one-period model with this a few extra side constraints is typically easier to solve than a 60-year model. And it may give some insight. That's a little bit harder to justify, but we'll leave it as that. So there's the idea of how you do it. You simply tie things together in that fashion. So let's talk about steady state solutions just a little bit more. So you know how to do it if you're using a linear programming type model. You just add this constraint that ending inventory equals beginning inventory. You can extend that idea a little bit more general. So if you're from a math background, you may be familiar with eigenvalues and eigenvectors. And in population models, for example, they have the following idea that to represent a somewhat busy system, you just simply define all of the various populations. So if it's cheese, it could be 1-month-old cheese, 2-month-old cheese, 3-month-old cheese, so forth, and you track inventories for them. Or if it's an animal population, you might have 2-month-old rabbits, 3-month-old rabbits interacting with 4-month-old foxes, 5-month-old foxes. And so you can perhaps put together some matrix which describes the interaction for them. And then the question is, can we, if we circle things around again like we did before and say we want, is there a solution where the state in period t is equal to the state in t minus 1? And here's how we transform from t minus 1 to a. And so if you generalize that, you say, can we get a solution something like this here, where the inventory levels in period t are simply equal to the inventory levels in period t minus 1 times some multiplicative factor lambda, which is typically called the eigenvalue. And so that's a standard problem in applied math, so it's interesting to have that sort of off in your back pocket to think about that way. And generally, there are as many different solutions to that equation as there are dimensions or states in the system. So it's interesting that for, say, the rabbits, foxes, clover population model, there may be one solution with lambda less than 1 saying that the stuff will die out, the whole system will die out with exponential decay. There may be another solution where lambda is equal to 1, where if you have this particular mix of the populations, it'll sort of stay steady. And there may be another solution where lambda is greater than 1, saying if you have this particular mix where there are perhaps a smaller fraction of foxes in the population relative to rabbits, the population will grow exponentially. So that's sort of another view of steady state results or steady state solutions. And I tend to do most of my work in Lingo. So in Lingo, there's an easy way of computing lambda, or eigenvalues and eigenvectors. There's simply a command called eigen where you can plug in a matrix, and you can do similar things in MATLAB. You name your favorite math system, there will always be an eigenvalue routine in it. And if it's a cyclic system, it may have both real roots and imaginary roots, and you can get all of those. So you may get some insight of, is it going to be a steady increase or steady decline, or is it going to be a cyclic system? So that's a bit about steady state solutions and an introduction to how to think about those. How about choosing end conditions? There are about 4 different ways of choosing end conditions. We already mentioned one, which is you simply chop off the model at the end and don't do anything else. And we said what's wrong with that is that it gives you the optimum way of going out of business in whatever your planning horizon was. Now, a slightly better thing to do is to put in primal limits. That is, you put limits on the inventories, the ending inventories at the end of the planning horizon. So for example, in the paint problem, they put some constraints on inventory there that the paint company said, we will not tolerate backlogging at the end of the 12-month period. Otherwise, you're cheating. You're borrowing from the future without having to repay. And so it makes sense to put some sort of primal limits on things. You may also want to put on salvage value, their dual prices, and say, instead of putting a limit on inventories, you say, inventory is worth this much at the end of the period. So quite some time ago, we were doing some work with folks who were scheduling what you might call a jet taxi service. And so you'd have a list of flights up for the next week, and then the question is, where do we buy fuel at each stop? Should we buy fuel? And it's interesting that the cost of jet fuel may vary by a factor of 2, depending upon which airport you are at. And so they fairly quickly observe that if you just chop things off at the end, all of the aircraft were running empty at the end. And so the question is, what is sort of the price of fuel that you should put at the end for valuing the amount of fuel that you have in the tank of each of the aircraft? And so what it really is, it's taking into account uncertainty. You don't know what flight is going to be done next a week from now, so you make a guess of what kind of airport you're going to end up taking that aircraft to next and what the fuel price will be at that airport. So one thing you could do for the salvage value would simply plug in the average price of fuel at the airports where you work and say, okay, that's the value of having fuel in the tank of these aircraft. Okay, another approach, not quite so obvious, is to stick on a steady state period at the end. And so that is, you put in one final period, and it is a steady state kind of period where you say, I don't know what the beginning inventory is in this period, but it has to be equal to the ending inventory of this final period. And so that is a way of handling the ending condition 1, where you don't put any explicit primal constraints or any explicit dual constraints, but you say you got to be stuck with that decision forever afterwards. So and that, in fact, is used by Carino et al. In a financial planning model for an insurance company in a real estate development, and by these folks in some modeling of General Motors production planning, where the planning horizon was 5 years, and then at the end of the 5 years, you stuck an additional year where you said the demand is going to be the same between Camaros and Suburbans and whatever thereafter. And then you're stuck with that. And then you have to do some interesting present value calculations to bring that whole cost back, because you're going out to infinity and you have to discount that infinite operation back. So modeling taxes. Here, if you just do it superficially, you may get tripped up a little bit. It's not very complicated, at least to a first approximation. And you simply have to have a curve, an equation that says profit minus loss equals revenue minus expense. and then realize that some of these are kind of interesting. What's interesting about expense? It generally includes depreciation, which is not a cash flow, but it's something that the IRS, the Internal Revenue Service, does take into account. So you have to add these additional constraints that do the depreciation calculations. And so here again it goes back to this doubly subscripted inventory variable that if you're depreciating assets, you have to have one inventory for every age class of asset. And then you may have to put in some complicated constraints depending upon whether you're using LIFO or FIFO depreciation or whatever. But the first approximation, you don't say anything about that. You let the model decide implicitly whether it's going to be LIFO or FIFO. And if it doesn't match what you claim you're doing to the IRS, you may have to add some additional constraints. So that's the basic idea there. The obvious constraints are the cash flow constraints. These represent real things, and you really do have to have those in there explicitly. Okay. Let's talk about an interesting kind of inventory, compressible inventory. So there is a firm in Chicago that's been doing multi-period planning for 25, 30 years. It sounds better, I guess, if you say they've been doing multi-period planning since the last century. And so one of the features is that they have to worry about having a supply of natural gas on the coldest day of the year, or whenever the coldest day appears. And you better have that natural gas stored in a reservoir that's under high pressure, because you have to pull it out fairly rapidly. You may have enough natural gas in inventory, but if it's in a low pressure reservoir, you may not be able to get it out fast enough. And so you want to worry about things. So let's look at how you model that sort of thing. So the feature is that it's harder to insert more gas into the reservoir the fuller it is, and it's harder to get stuff out when the thing is just about empty. And there are a variety of approaches that you can use here. And here's a linear approximation that's easy to think about. And you simply say, well, I've got a variable of the inventory in a specific period, and I maybe should have a second subscript on there, which is the reservoir. So you have one of these for each reservoir. And then the amount that you add each period, the amount that you remove at each period. And then a linear approximation is that the amount that you can remove in period t is related to the inventory level at the beginning of period t. So if the inventory level is fairly low, you can't remove it very fast. And so that's a nice linear approximation to these constraints on withdrawal and insertion rates. The insertion rate may not be quite as constraining, but the withdrawal rate may be more so. And then, of course, you have the inventory constraints there controlling the inventory. Precedence and resource constraints. Let's talk about these a little bit. And there are a number of situations in which you want to have these constraints in there. So for with regard to precedence constraints, what we mean there is that if you're tracking aircraft, say flying across country, you have to keep track of, you may have a 0-1 variable corresponding to which sector the aircraft is in. And you'll have constraints saying that it can't be in this particular sector unless it's previously traversed all of the preceding sector that it was supposed to be in. And then, of course, you have a processing time for each sector also. And there may be additional decision variables relating to which path do we take. In scheduling in a process inventory industry, you may have constraints that a chemical batch cannot enter tank J unless it finishes processing in tank J minus 1. In mining, which has been a big application for multi-period scheduling, if it's open pit mining, you can't remove a certain block unless you've removed all the blocks above it. And we'll talk about petroleum also, where there are similarly, or precedence constraints. So here is a situation, and let me first motivate it with a picture. So here is a picture, a two-dimensional picture, and a lot of minds use something like this, but in 3 dimensions. And so here, this block here is a very attractive block. And so how could you mine that block? There are 2 sort of pure ways of doing it. You could remove just the blocks on the left to get at it. That would be the fastest way to get at it. But what's a curious feature of that approach? You wouldn't have any useful ore until the very end. Whereas if you started from the right, it will take you a little bit longer to get to that really attractive block down at the bottom, but you do have some useful ore coming in a little bit earlier. And so increase this by half a dozen or a dozen so different blocks, and you can see what the planning problem is like. That you'll have forecasts ahead of what we think the demand for gold will be in each of the coming years, or coal, or whatever your favorite material is, and then you want to have a plan for how much, which blocks do you remove each year in each field or each mine. So how you do it depends upon your discount factor and also your concern about uncertainty. So in terms of doing things a little bit more explicitly, you essentially have to have constraints like this. So you're going to have a 0, 1 variable saying, did I remove block J in period T? And the simple way of writing it is that if I do that in period T, then in some earlier or no later period S, I had to remove the predecessor blocks there. So that should be Z sub I there. Okay, let's look at it a little bit more explicitly. And here I'll give a little sort of piece of advice on how to formulate it. So there's this challenge of, can we solve a model with all of the detail that was added to the model? So precedence constraints is one of them. So the obvious way of writing precedence constraints is like this. Well, maybe it's not so obvious, but it essentially says that if we're going to do block J in period P or earlier, I need to have done block I in P or earlier there. So the obvious way might be to simply think of that first, with all of that saying you have to do it earlier, but you can in fact add all of those in, and so you're going to have this constraint here for every predecessor pair for every period. And it's a pretty big constraint. So if you try to solve that, you might get mediocre performance doing it, because you've got a lot of constraints and they're pretty dense. They've got a whole lot of stuff in them, a lot of non-zero coefficients. They're sort of half-dense, as it were. That half of the matrix is filled with them. It's better probably to define a cumulative done variable, which is equal to 1. Again, it's a 0, 1 variable, if task I has been done in period P or earlier, else it's 0. And so it's simply related to the Z variables by this result, or in a cumulative fashion, WIP is related to WIP minus 1 by this fairly sparse constraint right there. So it's a fairly sparse constraint with 3 coefficients in it rather than n over 2 on average there. So for just solving the LP quickly, that's important. And so the precedence constraint then boils down to just this simple little constraint right there. That if I do J in period P, I need to have done I in P or earlier. I need to have done I in period P or earlier. And it's simpler algebraically, and also the branching in your integer programming solver also tends to be quite a bit better. That the branching decisions are more decisive. So that if you branch on a variable being either 0 or 1, that's pretty decisive. But if you branched on the original Z variables, if you set a Z variable to 0, that's not a very decisive decision. You're simply saying, I'm not going to do it in this period, but I could do it in a whole bunch of other periods. Whereas if you branch on the W variables, if you branch sort of in the middle, it says, well, okay, I'm not going to do it in the first half of the horizon. It's restricted to the second half. So it's like doing binary search to do things rather than linear search. And so that's why the performance tends to be 0. So I'll give a couple of other suggestions like that in the remaining slides of there's some things you can do to make the model easier to solve. Okay, petroleum. So if you are into petroleum production, so petroleum has 3 stages in it at least. There's exploration, which is where the high-risk guys are. There's production, where you're getting the stuff out of the ground. And then there's refining, where you're getting it ready for market. So here we're looking at the middle stage, which is production. And there's a fair amount of long-range planning here. So here you might want to plan ahead 20, 30 years. And what makes life interesting and why there are precedence constraints and resource constraints is that there are resource constraints in that the amount that you can get out is related to how many fields you have open in a particular period. But it's also related to the age of each field. And the age is measured not in calendar time, but in the amount of oil that you've taken out of the field or out of the particular well. And so the oil and the petroleum engineers have various kinds of decline curves, so-called, describing what happens as you pull oil out of the ground. And so it's true for various reasons for almost all wells that the production is fairly high at the beginning for perhaps a number of years, and then it starts to taper off, either in a convex fashion like this or maybe in a concave fashion. But there's some curve that they're pretty sure applies for every well in their portfolio. And they know when they're probably going to hit that decline curve for each one of the wells. And so they want to model that in their long-range planning models. And so the question is, how do you model a curve like that? And it's an idea similar to what we did in the mining one, that you put in some precedence constraints between these stages and say, if you're in this stage, you need to have finished that stage. If you're in that stage, you need to have finished that stage. So you put in some precedence constraints, somewhat similar to what we did for the mining one. They're a little bit more complicated because here there's going to be a continuous variable also involved, which is, we may have started this particular stage, but we may have turned off production this particular year because prices are low for various reasons. And so we're just not going to throw as much fuel on the market. So I'll give, how to do it. And for the curious, here is sort of what you need to do, but let me explain sort of qualitatively, and I think that's somewhat understandable, in that is if you start production in, say, the third stage, you're going to have a constraint saying that the cumulative production so far has to be at least equal to the previous stage. And so you just have to add in constraints that enforce that if you start production from a particular stage, you need to have exhausted all of the previous stages there. So these multi-period planning models, they have constraints on the production tied to the cumulative production, what goes on there. And that allows you to do that. And then they do some very interesting things with regard to uncertainty, which I'll talk about later with regard to how you handle uncertainty. Okay, so we talked a little bit about choosing a period length, and if you're of a mathematical bent, you might say, well, why don't you just make the period length smaller and smaller so that you approach continuous time? And so for many of these applications, you can in fact use continuous time models, and for some of these applications, continuous time models are more intuitive, and they're certainly easier to understand. So let's talk about a particular problem, and this is the problem of assigning jobs to machines, and also you want to sequence the jobs on the machines so that at any given instant on the machine, you've got a resource constraint. So when I say resource constraint, this is what I'm talking about, that you can't have more jobs running than you've got resources available for processing them. And so in the one machine case, you can't have more than one job running. There are no precedence constraints here, but there will be time window constraints. So there's a ready time at which the thing is available, and then there is a finish time on which you'd like to finish it. And you may assign a value to assigning a particular job to a particular machine. So what are some examples of that? Easy to understand might be assigning trucks, ships, whatever, to facilities. So trucks to terminals, or docks, I should say, at a terminal, ships to docks at a harbor, airplanes to runways, or airplanes to gates at the terminal, patients to hospitals, hotel guests to hotels, so forth. So this problem is fairly general in that sense of assigning tasks to machines with time windows. And so let's look at how we might tackle that problem. And let's do a fairly simple version of it. A one machine example where we're just assigning 20 jobs to one machine, and we need to sequence these jobs on that machine. And so you may have time windows on the machine, on the jobs rather, of what's the earliest you can start each job, what's the latest you can start each job. And so there is a textbook formulation of it where you have a 0, 1 variable for each pair of jobs, saying, either I precedes J or J precedes I. So that's one way that you could represent this one machine resource constraint to avoid conflicts there. Or there's a discrete time formulation, which is a little bit more complicated. And here are the results for this little one job problem. And let me tell you what the problem is, and then we'll jump back. So here's the problem. We've got 20 jobs. 18 of the jobs have a processing time of 5 minutes. One job has a processing time of 6 minutes. One job has a processing time of 4 minutes. And time windows are pretty simple, 0 and infinity. We don't care when it's done. Precedence constraints, no precedence constraints. The objective is pretty simple. I want to minimize the sum of the finish times. So if I've done a reasonably good job of explaining it, you should say that's a trivial problem. What's the order in which you should schedule those 20 jobs so that the sum of the finish times is smallest? Let me figure it out. I think you want to do that one first, do the shortest processing time first, and you want to do that one last, okay? So you throw this at your favorite solver, and if you use the continuous time formulation, it's probably going to take you greater than 60 seconds to solve that problem, which is kind of disappointing. Whereas if you use the discrete time formulation, it's relatively straightforward, solves in under a second. Similarly, if you want to sequence 55 aircraft with time windows at a dozen gates, that still solves in about 1 second with a discrete time formulation. It would be essentially let me not be too harsh on the continuous time formulation. You'd probably get a good solution fairly quickly in a second or so, but no guarantee of optimality. The gap would be quite large, and if you wanted to be convinced you had an optimal solution, you'd have to run it for quite some time. So let's talk a little bit about that. And so here is the continuous time formulation, which if you've seen it before, yes, that's the standard formulation, that the finish time of K has to be greater than or equal to the finish time of J plus the processing time of k times a 0, 1 variable if j precedes k. And so you got a bunch of constraints like that. And either j precedes k or k precedes j. And we want to minimize the sum of the finish time. So that's the standard continuous time textbook formulation, which is okay for a half a dozen tasks, not so good for anything larger. It's a little harder to explain the discrete time formulation, but it's not too bad. So I'll make one attempt, and if you're curious about this particular one, send me an email, and I'll include a fully detailed general purpose lingo model for solving that class of problems, and you can see the constraints with comments in them. But the basic idea is you discretize time. So here you use this GCD, what's the greatest common divisor? And here the greatest common divisor was 1 between 4, 5, and 6. And then you say z sub pt1 is equal to 1 if task t starts in period p. And then the resource constraint simply says I can be doing at most one task in each time period. And each task has to be assigned to some start and some time period. And that's the formulation. So this part here is not going to be obvious the first time around, but qualitatively it's doing the right thing. It says, look at all of the jobs that are in process in period P. The sum of those has to be less than or equal to 1. So whatever your favorite modeling language is, you can probably write a constraint that enforces that constraint. And that's a fairly good formulation that you can solve reasonable task assignment problems with that approach. Okay, I think that's it there. Let's talk a little bit about displaying results. And in particular, I'm going to talk about space-time diagrams and Gantt charts, and a little bit about time conversion routines. And so to motivate things, let's talk about something called the jet taxi problem. And so let me jump ahead just a little bit to give you a problem, or let me finish this here. So you have a set of flights you want to cover, and we call it taxi because you're given origin destination pairs of things that have to be traveled. If you're in trucking, it's a full truckload problem. And then you want to figure out how to route your planes and vehicles over these flights. And you're allowed to do repositioning or deadheading at some cost. And then how do we do that? Okay, so here is a problem. And let's jump ahead to the interesting stuff first, which that is a little bit harder. So take a look at that while I take a sip. And so I've got these 9 flights to be covered. And so, for example, I have a flight from Los Angeles to Salt Lake City that starts in 2018. November is the month, the day is the 5th, and the hour is this morning at 10 o'clock. So that's when that flight had to take off. So look at the rest of that while I take a sip. So that's the underlying thing that's driving the problem, and we're interested in how we can tackle that. And so we've got a travel time matrix. These are commercial aircraft travel times between the cities. And for our purposes, we will simply use the standard latitude and longitude information for each of the cities. And if you're solving a problem like this, what's the importance of this particular column there? You have to know the offset relative to Greenwich Mean Time here. And there's an additional parameter we put in there of how many aircraft we currently have sitting on the ground at various airports here. Okay, so that's the problem. So is it moderately clear what the problem is? So one of the motivations for studying this problem is to how do you present descriptions of these problems and solutions to these problems. So that's the data that's driving it. And here's some more data on it, travel times. And one way of presenting data is this geographic chart here, which is simply a collection of those flights that need to be covered, and with latitude and longitude presented on it. Now, is it pretty obvious to you of how you would go about routing the aircraft giving this presentation of the data? I think probably not. So let's look at what is called a space-time diagram. And so here is a space-time diagram of the flights that need to be covered. Okay? So time is plotted horizontally, and with some liberty, space is plotted vertically here. And so it's sort of appropriate West Coast, Midwest here, there. So it gives you a loose appreciation of distance. And so, for example, can you tell immediately whether you can cover all of these flights with one aircraft? The answer is no. Why not? You've got these two flights there, which are both in the air simultaneously. Okay, so you know you need at least two aircraft if you want to cover all of the flights. And then whether you can really do it feasibly with two depends upon things like the situation right over here. And that is, can you reposition that flight, that aircraft, to right there soon enough to cover that flight right there? So forget about, you're going to not do this one. You want to cover it with one aircraft. See what you can do with one aircraft. So clearly, you're okay there. And then you can probably reposition down there to cover that one. Then the question is, can we reposition for that one right here? So a space-time diagram does give you I think, a much better appreciation of that. So, we have that in lingo, so it's very nice if you can tie that to the solution that you get out and immediately throw up a space-time diagram of either the original data or of the solution. So let's look at the case where we allow two aircraft. So here is the optimal solution where we allow two aircraft, and we had various weights on the cost of an aircraft, the profit contribution from covering each flight, and things like that. And how many flights can we cover? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we were able to cover all of the flights, and we were able to reposition here from Salt Lake City to Denver to cover that flight right there. And let's see, so, and we had an aircraft here to cover that. And then here we did some fairly quick repositioning. So we did 3 repositions to cover all of the flights with 2 aircraft. So it gives you a quick way of explaining a solution to someone and showing what's going on. Now, how about one aircraft? What can you do? Or here's a solution for that particular one with 2 aircraft covering 3, 6, 9 flights, and it gives us the details on the repositioning flights. And then notice the nice thing here. For the repositioning flights, we tell you here is where the flight, when the flight should take off to do that repositioning. And so one thing I'll mention in another slide or two is calendar routines. It's kind of nice to have calendar management routines so you can do all of that stuff without too much thinking, so that you can present the time and the day of the week and so forth. So let's look at the case of one aircraft. And with one aircraft, we can cover 3, 6, 7. So we can cover 7 out of the 9 flights. And these are the 7 most profitable ones to cover. So if we're managing a fleet for Intel or whatever your favorite company is, it tells you which 2 aircraft you should go to, which 2 flights you should go out and rent a commercial carrier or go fly commercial to cover it. And that explains how to do it. Okay. Now let's talk about another kind of space-time diagram. And this is Gantt charts. So I suspect most of you are familiar with Gantt charts. So it's nice if you have a capability of being able to present results for not flights, but like this machine problem earlier in a Gantt chart. And for those of you who are familiar with the scheduling literature, this is the Fisher-Thompson 6 jobs, 6 machine scheduling problem. And if you use some of the ideas that we mentioned about a half a dozen slides earlier about how you use discrete time to represent some of these sequencing problems, you can solve a problem like this in substantially less than a minute and then present the results fairly quickly. And so you can play around with things and change some parameters and see how it affects the results quickly. And I also want to say a little bit about calendar routines, and notice that we can plot calendar time horizontally here of what's going on, as long as you tell the routines, you know, what's the unit of time of the things that you're processing. And here are the calendar routines that are implemented in Lingo. So you can do somewhat similar things in a number of other systems, but the basic idea is pretty simple and general. You need 2 routines, one to go each way. And so you've got one routine to convert year, month, and day to scalar time. So we have an internal variable, scalar time, which is measured in seconds, and you can measure it relative to whatever you want. And so there is a routine for converting year, month, day, hour, minutes, and seconds to scalar time. You can do that. And you can then do arithmetic on it. You can add travel times, delay times, whatever. And then when it's time you have to display a report, you just go the other way, and you go scalar time to year, month, day, minute, seconds, and you fill in that vector right-hand side. And so that's how we got the output there. So we did the calculations internally in the obvious way of adding on travel times when we're doing the optimization and so forth. And then to write out the chart, here is what the space-time chart looks like. You tell it what the labels are, and then you give it the as many different types of arcs that are in the problem. So there's the loaded set. Here you list the pairs, the origin destination pairs, the start time, the leave time and the arrival time, the departure time and the arrival time for each pair, and similar for reposition times. And that's what gives you this chart here, where you've got some red and some green arcs there. So fairly simple to do those sorts of things. Okay, what else do we need to talk about? So we talked about that. Choosing an objective function. For most multi-period planning problems, the objective function is to maximize the discounted present value of the contributions in each year. It's quite easy to generalize that slightly. So you have period-dependent rates. So if you look up the current rates on zero coupon bonds, you can plug that in for, well, you can't plug it in quite. You have to compute out the ahead interest rates for each period, and then you can do the per period interest rates. Another complication you might do to it is if there's uncertainty, so we'll talk a little bit more about uncertainty, you may plug in a risk-adjusted dependent rate. So in that expression right there, you may add for various items, you may add an additional term there. You adjust the interest rate a little bit depending upon the uncertainty of that particular one. So that's one way of handling uncertainty. And you may use a utility function if you're using scenarios that if you have multiple scenarios and you say, well, this could happen or that could happen or that could happen, they have different cash flows, and you may want to apply a utility function to it that has the right behavior. There's a well-known quote by Warren Buffett that says the product of a long set of really big numbers that just happens to include 1 0 is always going to be 0. And so using a utility function takes that into account a little bit. And the most common utility function is downside risk. So let's talk about that a little bit. So if you're going to use a utility function and you want to look up utility functions, sort of the standard thing is downside risk. That's most easy to understand in the C-suite. And that doesn't mean the folks who do the programming. It means the executive level, and they can understand downside risk. In banks, they like to use value at risk, and it essentially means that you have an objective function that looks a little bit like this. You want to maximize the expected wealth minus some weight, like the 95th percentile standard deviation applied to the standard deviation. And then the most general one is power utility. So if you need to look up more general ones, that's the one to look at. It's quite general. It includes log utility. So supposedly Ed Thorpe, when he did his gambling, beat the dealer in Las Vegas, effectively was using a log utility function because he had to the decision he had to make in playing blackjack is bet sizing. Of how big a bet should I make on this particular play based on one, what my wealth is, and two, what I think is the probability that this thing is going to pay off. So he adjusts his probability that it pays off based on card counting and what he thinks is going to come up in the draw. And so a log utility is what he used there. That's officially what I'm going to present in slides. I'll mention a couple of other things, given the extra time, that with regard to uncertainty, a standard thing that is done, let me phrase it this way. Sort of the gold standard of modeling uncertainty is stochastic programming, where you identify a scenario tree of what can happen, and for each period you have a set of decisions of what you can do, and the decision each period is conditional on which branch of the scenario tree you happen to be on, and then you maximize your utility function, typically maximize expected present value over that. And so you can really represent all kinds of uncertainty quite well. But what's the problem with that approach? It's because you're dealing with a tree, and so the number of branches in the tree grows exponentially with the number of periods that you have in. So if you use stochastic programming, typically you'll see it's only done on two-stage problems or two or three-stage problems, and it can do a very nice job for that. For multi-period ones, it tends to be out of hand for that. So what do people do in practice? So here's what some folks in the petroleum industry do. And well, let me first describe it for electricity generating. So the standard thing there is sort of what you might call robust programming or robust optimization, a variation of that, in that there are regulations effectively that says a given market has to have a certain amount of so-called spinning reserve for each hour. And a spinning reserve means we've got these generators up and spinning, but they're not producing very much electricity, but they could produce a fair amount of electricity fairly quickly. And so if the spinning reserve is 20%, it says we could, in just perhaps a couple of seconds, depending upon the type of generator, get 20% more capacity in this particular period. So that's one approach which works in a number of industries. So if you think of the mining problem, how might you handle it there? One approach would be stochastic programming. If you just split things into this year, and then the second period is all years thereafter, and you could have probabilities on each branch there and use that. The other alternative is that you could say, I want to have enough ore bodies that are within one period of being opened up, have a certain amount of those at that capacity in each period. So you can put in a constraint of how much I could open up in 1 year if need be. In the petroleum industry, the similar thing to the spinning reserve is in each period you say, okay, here is what my forecasted demand is. I want to have enough wells started, so I've got a decision called production. So I maybe have the production variable at 0, but I know what stage that well is in, and so I know how quickly I could bring that well up to how much production is in. So in doing the multi-period planning, you may put on some additional capacity, or what you might call spinning reserve capacity constraints. And so that's a standard way of handling uncertainty. So, but the gold standard is stochastic programming, if you can do it, but if you need to do many periods ahead, that's tough to do. So I will call it, I'll declare victory at this point. Any questions or comments? So I missed a fair number of things I didn't cover, so if you feel that they should be covered, please raise your hand and exposit. Yes?
In a less truckload problem, how would be the constraint different?
In which problem?
Less truckload, LTL.
Okay. That one, you've got me. So I think the question is, if we have this problem here, is that the one you're thinking of? Yeah. So what would be the uncertainty? So here might be one form of uncertainty, is that here we're planning ahead 1 week, and so here is what Federal Express supposedly does, and I have not checked recently, but the uncertainty with Federal Express is what on a given day? One is they're not sure what the demand will be of how much stuff they have to bring into Memphis or wherever, and the other form of uncertainty is that a plane may break down and say that they don't have as much capacity as they thought. And what they supposedly do is that they position 1 or 2 planes strategically somewhat far away, if Memphis is the hub that we're thinking of, somewhat far away from Memphis, but close to demand points, so they can fly that plane into whichever site needs the extra capacity. So if you're using a stochastic programming approach, you would say, okay, here are the scenarios. So you could do a 1-stage or 2-stage stochastic programming approach. And say, here are the scenarios of where we could have plane breakdowns, or where the demand at a given airport is bigger than 1 plane load. And then the decision is, how many planes do we position at each place? So stage 1 is we decide where to position the spare planes. Beginning of stage 2 is we find out which planes broke down and which cities had the high demand. And then the end of stage 2 is the decision part. The recovery part is we have to fly those planes in. And the measure of performance is what fraction of the shipments did we nevertheless get into Memphis on time, given this particular positioning of planes. So that's how I think I would do it. Is that what you were thinking of? Yeah.
Even this can be treated as a LTL problem. Supposedly, if Los Angeles is the starting point, and the entire set of cargo that is one aircraft loads into the final point at Salt Lake City.
Yes, that's an interesting point. So the comment is that you might be able to also do better, and so this is sort of thinking outside the particular box that I was in that you could use one aircraft to pick up folks and sort of do it's not Uber, but it's one of the cheaper sort of routing systems where you share a ride. And so folks do that. I've seen it done with, say, helicopters, where you're hauling people from various well sites. And some folks from this well site have to go to that well site, and so you're given all of arrows sort of like that of the origin destination pairs, and say, and you know how many people have to do, and your helicopter carries 20 people, how would you route them in sort of the way that he suggested to pick them up, not exceeding helicopter capacity, so forth. Similar thing for picking up of milk at dairy farms, in that some of the farms have full trucks to be picked up. Others have a third of a truck, a half a truck, so forth. Okay? Any other comments, things that we've missed? Yes, in back.
In the scheduling problem, have you tried to change the objective function? For example, the computation time instead of the sum of all the computation times? I don't know if you understand that.
It was one of the problems I discussed earlier.
Yeah, in the scheduling.
The task to machine assignment? Uh-huh.
You compare the times to get the optimal solution between discrete time formulations and continuous time formulations.
I'm sure I have at one point, but if you, it certainly depends upon the solver. Okay, so here is the continuous time formulation. So your question is,
If you are trying to change the objective function.
Okay, yes. I don't think I have checked that out. My intuition is that the objective function would not make a big difference. So here, the objective function was to minimize the sum of the completion times. A more common one is perhaps to minimize the maximum completion time, which was the objective in the 6-job, 6-machine problem. And I'm not completely sure. My intuition is that the minimize the maximum time would be harder, but I'm not completely sure. Do you have some insight that would tell us? Yeah.
I'm just curious if
Yeah.
there is some difference between continuous time formulation and discrete time formulation.
I've tried different objective functions for the discrete time formulation, and it is fairly insensitive to the objective function. The min-maximum objective seems to be harder than just minimize the sum of things. And part of the reason why the min-max objective function tends to be harder for integer programming solutions is that there may be lots of alternate optima. And so if there are alternate optima and the bounds are not very good, it'll waste a lot of time pursuing these alternate optima, and that takes a lot. So that is why the min-max objective tends to be harder, I think. But don't take my word for it. Yeah, okay. But for the standard continuous time one, I've tried it on a number of solvers, and every solver has a hard time with the pairwise comparison continuous time formulation. Okay? Thank you very much for your attention. I appreciate your attendance, and please let me know if you have any other questions. Okay.